we are delighted to have our own Dr. Venkata Sriram Siddharth Nadendla, and he goes by Sid, as this morning speaker. He is an assistant professor in the computer science department at Missouri S&T, starting fall of 2018. Prior to that, he was a postdoctoral researcher at Urbana-Champaign, University of Illinois at Urbana-Champaign. And Dr. Nadendla received his PhD degree in ECE department from Syracuse University in 2016, his master's degree in electrical engineering from Louisiana State University, and his bachelor's degree in electronics and computer engineering from a university in India. He has worked during his PhD student time at a Rome lab in New York, and his research interests span the fields of trustworthy AI, cyber-physical human systems, algorithmic game theory, wireless networks, and security. So without much ado, let us all welcome Dr. Nadendla. Sid, the podium is yours.
Thank you, Professor Das. So I originally gave a different title to my talk. I thought I have a better title now, which is Fair Perceptual Learning for Trustworthy Socio-Technical Systems. So without much ado, so I call my lab team as Cyber Physical Human Systems Laboratory, primarily because we are interested in three entities. One is the cyber infrastructure, which has to do with various aspects like resource allocations, communication, networking, so on and so forth. And then you also have physical infrastructure on the other side, which collects data through sensing infrastructure, and also makes controlled decisions or interventions through actuators. And the third entity is people, which could be users of these systems, or which could be workers who are a part of the system. Now, any interaction between any of these three, or two of them, or three of them together is what we call a cyber physical human systems, or cyber physical, cyber human, or human physical systems. And some of the examples here are listed in front of you, and we are pretty much interested in problems that span across the spectrum. Now, the team comprises of a diverse set of students. So I have two PhD students directly working under me, three being co-advised, a couple of them being from mechanical engineering, which is why I said diverse. And I have a bunch of master's students and bachelor students, and whatever work that I'm currently doing here is all because of them. And so I should certainly acknowledge their effort here. So to give you getting back to the topic that we're discussing today, what are socio-technical systems? Now, a socio-technical system is basically any system where people and machines interact with each other. And machines can be robots, recommender systems, some sort of an AI algorithm, whatever it may be. And examples include, for example, to the left, you have this example here where we are dealing with content moderation systems. To give you some context here, people typically post content on social media, and not all content should be admissible, because some of this content could have extreme information. I mean, extreme information that might have hate speeches, that could have very violent images, and so on and so forth, which is not something that you want to reveal to everyone out. So content moderators typically sit and sift through this information, online data, and then they decide whether a particular post is admissible or not. And unfortunately, these moderators their job is so undervalued that they don't get enough benefits. And looking at such extreme information for such long periods of time, they go through a severe amount of trauma, mental trauma. And people actually start experiencing PTSD-like symptoms within 3 months, within the first 3 months of their job. And so people leave the jobs, and there is always a continuous turnover in the workforce within the content moderation industry. And it's turning out to be a very unsustainable industry. So the solution that's being offered currently is we have these AI-based systems that try to solve a part of this problem and then make the content moderator's life easy. But again, it can only do so much because moderators are the one who can actually make reliable decisions. Now, another application that you can think of where socio-technical systems are applicable is in medicine. So for example, doctors perform robotic surgeries today. You can also have robot assistants taking care of patients or senior in senior living facilities. You can have prosthetics where a part of your maybe the patient might have lost a limb, and the question is, how can you make sure that this limb communicates to the brain and the person can actually control that limb, mechanical limb, automatically. And so it's a case with diagnosis. So you have human robot interaction in medicine, and a completely different application could be intelligent transportation systems, where today we talk about connected and autonomous vehicles. And these connected and autonomous vehicles interact with each other. So that's the cyber physical infrastructure part. But there are also people who are commuting in these vehicles, and they have their own preferences. So the interaction between people and these connected autonomous vehicles, and in fact, any infrastructure out there within the intelligent transportation system, all of this broadly falls under socio-technical systems. Now, one of the main issues that socio-technical systems face is the lack of trust. So people actually can lose trust very easily in socio-technical systems. And there are many reasons why trust can be lost. So one of the first reasons is security threats and vulnerabilities. So you can easily hack into, let's say, some system and then either steal data or introduce some sort of a malicious control, and then that can that automatically affects the trust in the system. Now, I would like to label each of these factors using a single word, and which is why I have them in the brackets here. So anything that has to do with security threats, vulnerabilities, privacy concerns, all of them I labeled under the word robustness. Now, people may use this word differently in different contexts, but this is what I'm doing here. Now, the next issue is reliability. So for example, you may come up with a certain performance guarantee to a system, but if it doesn't offer that, then people may lose trust in such systems. So here is an example of a Tesla autopilot, which actually made a mistake and a person lost his life. And the sad part was this very person who lost his life in March 2018 gave a complaint to Tesla saying that there is a problem with the autopilot, and it is the same problem that led to this accident and the person died. Now that incident actually changed everything with Tesla and its sales, and people started distrusting self-driving cars. So another example, another factor that can affect trust is explainability. So imagine that you have a very complex today we are all talking about deep learning, which involves deep neural networks, which are very complex architectures. And all we do is, so in the context of medicine, for example, here is an X-ray of a patient, a chest X-ray of a patient, which you can throw into some deep neural network, and then and tell whether this particular patient has COVID-19 or not. Okay, and this is an example that one of my students did a few months back. So the problem is, why should a doctor trust this diagnosis? So just because some arbitrary algorithm comes up with a diagnosis saying that this person has COVID-19 doesn't mean the person actually has such a disease. So that's when we need some sort of an explanation as to why that particular algorithm came up with such a analysis or an inference. And in this context, we came up with some you know some explanations to this picture. And for some reason, this particular picture, you can see that these features mattered in this diagnosis. And in fact, this person had COVID-19 when this X-ray was taken. So based on these features, our algorithm was also able to detect that this particular person has COVID-19. But just by looking at X-rays, it's hard to tell whether this person has COVID-19 or not, right? So that's one of the factors that can affect trust, complex system design. Now, another major factor that can affect trust is misaligned motives. So let me explain this in the context of an example, and you'll better appreciate this. So here is Waze, a navigation app that's presenting some route recommendation. And the original route is supposed to be this orange route, and there is some congestion here. And therefore, Waze is now suggesting an alternative route. Now, the question here is, if I were using this app at this point of time, would I in fact take this alternative route? Maybe this particular road is not well laid, there are a lot of potholes, and I just changed my tire wheels. I may not be happy with that recommendation. So I would automatically ignore this recommendation and continue in spite of having a congested road, right? Now, another alternative reason why I may reject this particular route alternative is because this particular road is unsafe. Um, so the problem is, people here, the person here, which is myself, has a fundamentally different motive compared to what Waze is looking at, because Waze is only looking at this problem from a travel time perspective. But I, as an individual or a user, is doesn't just care about travel time. I have many other attributes to worry about. Okay. Another example is Bitcoin mining. So for example, Bitcoin mining is designed to promote decentralization, but miners, because they're selfish, because they want rewards, they tend to pool together, and then the whole concept of decentralization, um, is questioned in Bitcoin because of this sort of misaligned motive problem. Now, another factor that can affect trust between socio-technical systems is agent interdependence. Now, so for example, there's a disaster. In this context, I've taken a disaster inside a mine. Assume that this mine is 1 kilometer underground. And so some fire or some explosion happens. There is this disaster, and miners would like to escape, but they do not know what the situation of the mine is. So therefore, they have to interact with the technology out there inside the mine, team up together, and the technology needs to solve one part of the problem, which is about performing surveillance, and people have to listen. But under stressful scenarios, that may not happen, and which is why agent interdependence is very, very important to ensure trust in socio-technical systems. The next factor that can affect trust is inaccurate mental models, which I call as perception. Now, imagine that you have a self-driving car, and the self-driving car is taking you in a certain manner, but you may not be happy with its decisions because uh, the self-driving car did not do a good job of estimating what your needs and desires are. Now, that inaccurate mental model about the owner of that car actually can lead to lack of trust. So your learning algorithms have to be good at learning what the user's needs are. Now, finally, another most important factor that can affect trust is fairness issues. So if there is bias in the algorithm, so if the algorithm prefers one group over another group, so in this context, the group is race, in this context, the group is gender. So if there is gender bias or if there is racial inequalities within the service offered by the algorithms, then people lose trust in those systems. Now, while there are a lot of factors that can affect trust, today I'm going to focus on the last two, which is why I've changed the title to Fair Perceptive Learning for trustworthy socio-technical systems. Moving on, there are a bunch of projects that we're working on in our lab currently. But today, for the sake of this talk, I'm only going to focus on these two talks here. So one project is related to worker health, and another topic is regarding algorithmic fairness. So starting with the first problem, which is regarding worker health. The title of this topic is, or the subtitle of this topic is predicting stopping time in worker task decisions using discounted satisficing under cognitive atrophy. So to give you some context here, this is more about workers performing repeated tasks and workers getting tired after a long day of work. And so automatically their ability to work goes down drastically, and very quickly they may stop working. The question is, how do we learn the worker's cognitive atrophy, and how can we predict the worker stopping time? And it has many applications. So for example, in the context of content moderation, a content moderator can keep looking at content one after the other, a post after post after post, and maybe after a few posts of which have extreme content in them, the worker is extremely tired mentally, and so he may give up for that day, right? Another example is ride sharing, where taxi drivers keep taking rides all the time, and if they continue taking rides for a long period of time, they may get tired. So the question is, when do they get tired? So is the case for production line workers in industry. Now, this work is something that one of my students, Monica, a master's student who graduated in summer, did, and we are still improving this. I mean, we're still working on it towards the journal paper. So let's get into the details of what this topic is about. So to begin with, repeated task decision models are typically modeled as using regret minimization frameworks. Now, this works in the case of machines because we typically model machines as some sort of a framework that optimizes, or say a framework that solves an optimization problem. Now, but people are known to deviate from optimization models. This is a very classic, knowledge that's available from the psychology literature. We don't typically try to optimize any objective function. So from 50s onwards, 1950s onwards, there has been a lot of work on bounded rationality models. And one of them is satisficing heuristic, which tells that a particular worker, chooses a task as long as he gets a certain reward that's greater than a threshold. Otherwise, he won't work. Something like that. So there is a threshold-based decision rule that's being employed by the workers, and not an optimization framework. So they're not trying to maximize reward here. As long as they get, let's say, $100, they're happy. It doesn't matter whether they'll get there is another task out there which can give them $1 million. As long as they get $100, they'll be happy. Now, but people exhibit cognitive atrophy over time. The question is, cognitive atrophy meaning Maybe at the start of the day, the person is energetic, their output is high, whereas towards the end of the day or maybe in the late afternoon, they'll be tired and their performance goes down. Now, this has a negative impact on worker health um, if you don't assign tasks properly. And it also affects system performance because workers are not able to perform well. So the question is, how do we learn this behavior? And so the assumption that we came up with, so we propose a novel heuristic called discounted satisficing. Uh, the assumption is that workers typically make decisions in two stages. The first stage is whether to continue working or not. And the second stage is once they decided whether to continue, which task to choose. Now, we are not going to focus on stage two because there's a lot of work out there on stage two. People have come up with many different learning algorithms or models that mimic human decision making when it comes down to task decisions. But there is no work out there on stage one. So we're going to focus only on stage one here. So because we only focus on stage one, we assume that the outcome of stage two is a multi-attribute reward. So we assume that there is a set of attributes A that the worker cares about. So if I'm looking at a work, it's not just, so it's a type of work and many attributes that he may be looking at. Okay. And these attributes are somehow combined linearly, okay, using a weight called alpha j. And this is the utility of that particular worker at time t, given that he picked that particular task. Okay. Now, the way we model this behavior, the way we model cognitive atrophy is, as time progresses, the worker, if he decides to continue, he picks a task, he gets a utility in return. And these utilities accumulate over time. So this is the accumulated utility, sum over all t's. And as long as it is less than some beta to the t minus 1 lambda, he will continue. If the moment it is greater than or equal to beta to the t minus 1 lambda, he will stop working. Now, lambda is the threshold that they start with, okay? And beta is the discounting factor, which is why we called it discounted satisficing. So in a regular satisficing model, you don't have this beta to the t minus 1 term. You just have lambda. But now you have this dynamically changing threshold over time. So as time progresses, I may initially think that I'll be happy with $100, but as time progresses, I may be satisfied with even $10 if I'm not getting enough money after a long days of work because I'm getting tired. So that's what this beta captures. So that's the cognitive atrophy variable here. So if you look at this model, you have three different types of variables. One is the attribute preferences. The next is the discounting factor, beta. And the third is the satisficing threshold. We can always observe what T is, what T star is. T star is a stopping time. When does the worker stop? Okay. So now, so the question now is, how do we estimate alphas? How do we estimate beta? And how do we estimate lambda? So to begin with, let's take a simpler setting. Okay. Now, let me take a step back. Note that this is a highly nonlinear model, and it is not an equation. It's an inequality. It is based out of a bunch of inequalities. Okay. So each inequality is, I mean, you have an inequality for each time. And then you also have, you know, so at the final so the initial few inequalities, this will be less than the threshold, but at the stopping time, it will be greater than or equal to the threshold. So you would have a system of nonlinear inequalities as your model, as opposed to the standard equation based models. So to simplify this problem, let's start with a single attribute case. So meaning there is only one attribute, you don't have multiple attributes, so you don't have to worry about alphas. So now you only care about betas and you care about lambdas. So you don't have this term here, you only have these two variables. Now, luckily for us, if you look at this model, if you apply logs, this becomes a log linear inequalities, right? So when you apply logs, this is how the inequalities look like. So for the first t star minus 1 terms, the threshold won't satisfy. At t star, the stopping time, the threshold satisfies and the worker stops. So these are the inequalities that have to hold simultaneously. And if you notice, each of these inequalities in the log beta log lambda space, these are linear equations. So these are half spaces in some sense. Okay. And so when you look at all these inequalities have to satisfy simultaneously. So what happens is these half spaces overlap with each other, and what you get is a convex polytope. So at the end of the day, you would end up with a convex polytope from a given worker. And a simple estimate to what lambda beta may be is to take the centroid of this convex polytope and say that that would be a potential lambda beta that satisfies the worker's behavior. In fact, any point inside this convex polytope satisfies these inequalities, right? But for the sake of simplicity, we just took one point, which is a centroid. And it so happens that this particular algorithm works quite well. So especially when beta is greater than 0.5. So you can see that the error in lambda and the error in beta both converge to 0 very quickly. So within a span of 5 days, your error is close to 0. So all you need is data for 5 days, and you can estimate a worker's model very quickly. Now, and so is the case with stopping time prediction. So the blue curve here is the stopping time prediction, and even that is very, very close to 0. Now, unfortunately, the same algorithm doesn't work when you have beta greater than smaller than 0.5. So here is an example where beta is 0.35, and neither does lambda beta converge, nor does the stopping time converge. So this algorithm, I'm just showing you one specific example, but we have worked out this particular algorithm over different possibilities, and it typically works for scenarios where beta is greater than 0.5. Beta is a cognitive atrophy model, meaning if you don't get fatigued quickly, then beta is greater than 0.5. If you get fatigued very quickly, then beta is less than 0.5. So, so if you're a normal person who can endure a little more time, then you can be predicted very, very easily. Now, in this particular simulation, we assume that the reward distribution comes from some gamma distribution, and we also assume some bounds, and these bounds are reasonable bounds because we just looked at beta being between 0.05 and 1. Beta normally lays between 0 and 1. And we have to do this because log beta tends to minus infinity when beta tends to 0. So now, does this work in real life? Now, so for that, we designed an app. And this app is a simple game where you get to choose one of the bandits, the 4 bandits. And as you keep clicking on one of these bandits, you get a reward, and this reward accumulates over time. And you're free to stop at any point of time. And this app records all of that information. Okay. And the result that we have is we were not able to predict the stopping time very well. Unlike the simulation results, when we actually took this experiment to real data, we only could get 26% accuracy. So the question is, why did it not work? And so remember the assumption that we made about the number of attributes. We only assumed single attribute, right? So maybe because we assumed that workers make decisions based on single attribute, our prediction accuracy was so low, which is why we switched to multi-attribute case. So moving on to multi-attribute case. So if you notice how this problem is, the multi-attribute case is highly nonlinear, and it is so you have some variables inside the log term, and you have log beta here, log lambda here, and you can always introduce slack variables to make these inequalities into equations. Okay, and then model this as a standard regression problem and solve this regression problem. So your objective is to minimize the squared error, and you just have to make sure that each of these quantities. So for example, log beta, because beta lies between 0 and 1, log beta is always between -infinity and 0. So log beta is less than 1. Log lambda being greater than 0, it can lie anywhere between -infinity and +infinity. And so you have all these different scenario, conditions that you have to take care of. And these are the slack variables. S's are the slack variables. You can solve this problem. Now, linear regression, this is a simple quadratic program. There are very nice, powerful interior point algorithms, and we can use interior point algorithms to solve this problem. Okay. So I'll present the results towards the end. I have a few more algorithms to present. So this is batch learning. So this is assuming that you have data coming from a worker over a day, and you have many such days of data available to you. So this n here represents the day index. So you have a huge data set out there, and you're solving this particular regression problem over the entire data set in one go. And the problem is it actually converges very slowly because the size of this problem is very large. So which is why we switched on to another approach, which is an online learning approach. So we assume that data is coming one day at a time. So we get a day's worth of decisions at a time, and based on this sequence of data, how do we learn over in an online fashion? So we came up with two different methods: online learning based on bounds, online learning based on quadratic program. This approach, the online learning based on bounds approach, is based out of the first idea that we have. So you get this convex polytope, if you remember, for each day. For that convex polytope, you can come up with minimum and max, so upper and lower bounds to the values of beta and lambda. And then you can update those bounds as you get more and more days, and you can get better and better updates. Okay, so by doing that, we get a certain algorithm. Now, similarly, similar to the batch learning approach, we can actually come up with a squared error for one single day, data available for one single day, and then we can resolve that problem every day. But this particular approach doesn't work unless you introduce this regularizer term, which says that you cannot switch your estimates drastically. So your past estimate, your estimate at I-1, at time I-1, or day I-1, and day I have to be similar to each other. You shouldn't have a big jump. And as long as you introduce this regularizer term, this algorithm works well. And the summary is, so again, we have an algorithm for that. And the summary is, all these algorithms work very well when beta is greater than 0.5. So you can notice that the left side here is the prediction time error. So all these prediction times work very well. The only thing that takes more time to converge in terms of number of iterations is online learning with quadratic program, because of that regularizer term. But if you look at this batch learning approach, each iteration itself, because we are looking at this as a whole data set perspective, the algorithm takes a lot of time to convert. So although these are number of iterations, these iterations are days. But the runtime of this particular algorithm is way higher than the online counterparts. The same is I mean, the same is true even with lambda and beta errors. The lambda and beta errors are also very close to zero. I mean, so we still have some bias, but that bias is so small, it really did not matter much. We are doing quite well in terms of the performance. Now, the problem is with the case where beta is again less than 0.5. Now, with beta less than 0.5, our prediction of the stopping time is doing well, because if you look at the stopping time error is actually converging to zero very quickly. But the problem is we are not able to estimate lambda and beta properly. So we come up with a wrong lambda, wrong beta, but somehow this wrong lambda, wrong beta are able to explain the same stopping time very efficiently. So while we are able to predict worker stopping time very effectively, we are unable to explain what their mental state is when beta is less than 0.5. So that's the case with known multi-attribute weights. Now, how about when you do not know multi-attribute weights, when you do not know alphas? So now alphas are also in the problem. So the goal is to minimize a root mean squared error of in terms of stopping time. And we want to minimize this objective with respect to lambda, beta, and alpha. Okay. The problem is highly non-convex. It's very difficult to solve. So we came up with an approximation, and the approximation that we came up with is called alternating minimization. So we assume that alpha is available from the previous iteration, and then we minimize this objective with respect to lambda beta. And this is very similar to one of the previous algorithms that we had. And then once we have lambda beta estimates, we use that lambda beta estimates, and we minimize the same objective with respect to alpha. Now that will give us an alpha estimate, and both of these independently are convex optimization problems. You can solve them very effectively using integrated point methods. And we have an algorithm for that. And the results to this algorithm is also quite interesting. Now, whether we have beta greater than 0.5 or beta less than 0.5, the stopping time actually converges to very close to zero. But we are not able to bring down the error for lambda and beta. So lambda beta error terms are quite high for both the cases. So in other words, in the case of unknown multi-attribute weights case, it's just not possible for us to explain or to learn what the worker's mental state is accurately, but we can certainly predict their stopping time very accurately. Now, currently we are, so this is what we have done so far. This is what Monica has done in her thesis. What we are currently doing is we are taking these algorithms and we are testing it on taxi trips data, which is available from Chicago's data portal. And this data set is updated every few days. And we have data from 2016 all the way till now. And we are looking at how our algorithm is performing on that data. And the reason why we particularly choose this data set is because we have taxi driver ID. So we have data available for each driver, which is typically not available in other data sets for the sake of privacy reasons. So the next set of work that we are currently looking at is, are there any novel behavioral models that can better perceive workers' mental status and maybe even accurately predict worker stopping time? And then can we test our algorithms on diverse scenarios? So here is Chicago's data portal on taxi trips. But what if I have content moderation data available? Can our algorithms work on those data sets? Or what if I have a production line workers data available from some industry? In which case, can I test it on that? So we're trying to look at different diverse scenarios depending on whether the data is available or not. And finally, we also want to compare the prediction to model agnostic approaches. Now, once we have this model, what do we do with this information? So the next step is to design appropriate task recommendations so that you can help worker, uh, not to, get affected by this workload, but at the same time, improve system efficiency. So we are looking at these micro task recommendations at this point of time. Um, but I don't have anything significant to talk about, which is why I kept it as ongoing work. Um, so this work, whatever I presented, a part of it, at least the single attribute case, was published in HComp 2019. And if you're interested, I can share you this draft. So this is the first part, which is about inaccurate mental models about the workers. So if you have, so since I'm running out of time, I'll probably continue. If you have any questions, please feel free to post on chat and I'll address them towards the end. So the second part of the work is about fairness, algorithmic fairness. And this is a problem that has been haunting computer scientists' minds for the past 3-4 years now. And the question is, there are many recommender systems out there which are designed based on machine learning approaches, and they're deployed in applications such as criminal justice law. Today, judges use machine learning algorithms to decide whether a person can get bail or not. Similarly, there are realtors who are using machine learning algorithms to decide which house to show to whom, if they were to go for a rental house or if they were to go and buy a house, whichever it may be. And then there are banks which are using machine learning algorithms to decide whether a person can get a loan or not. So all these three applications have been observed. So all these algorithms have been known to show biases, exhibit biases with respect to race, with respect to gender. And the question is, how do we solve this? And this is something that one of my students, Mukund, is working on. So to give you some context here, machine learning algorithms exhibit discrimination. Although they are algorithms, they do exhibit discrimination. And that's because they're trained on some bias data. That could be one reason why you can have biases in machine learning algorithms. Or another reason is because the objectives that you've chosen to train that particular data, the objective function, the loss function that you've chosen, is myopic. It doesn't capture all the attributes. And the third one is when you ignore what people's needs are. So if social preferences are something, but if you optimize your algorithm based on if your algorithm is offering something else, then there is this mismatch, and that can lead to discrimination too. So here is one example to the right. So Compass is an algorithm, is a tool that's used by judges in Florida. It's currently being deployed. And it's basically a machine learning algorithm that takes in a particular prisoner's profile and decides whether that particular prisoner can get bail or not. And to give you an example of the biases that it can show. So here is an example where this particular person to the left, a Caucasian male, was given a score of low risk, which is 3. Okay, although he has prior offenses of 1 domestic violence, aggravated assault, grand theft, petty theft, drug trafficking, so on and so forth. And he was given a bail, and after giving a bail, he immediately committed another crime, which is 1 grand theft again. On the other side, you have this, African American guy who is rated medium risk with a score of 6, but all he had is a prior offense, which is 1 petty theft. And after giving him a bail, there was no subsequent offenses, so there was no recidivism. Now, these scores are given by this Compass tool. Another example is with respect to, so that's with respect to race. I also wanted to give you another example, which is with respect to gender. So here is a Caucasian male, again, given low risk scores, although he committed some 2 armed robberies and 1 attempted armed robbery, significant felonies, On the other hand, you have a black female here who received a very high risk score, although she just committed 4 juvenile misdemeanors and never committed a crime after that. Now, these are the kinds of biases that we're talking about. And the question is, how do we mitigate this sort of a discrimination within this ML algorithm? And the challenges are, and this particular problem is not just within the context of criminal justice. You have, discrimination in healthcare. Machine learning algorithms show discrimination in healthcare. They show discrimination in recruiting, job recruiting. They also show bias in terms of mortgage, banking sector, and so on and so forth. So the question now is, how do we solve this problem? And unfortunately, to address this issue, fairness is a notion that's very, very contextual. It is very dependent on the context, and it is very subjective. So you really cannot automate it. And two, there are conflicts between different types of fairness notions, which we will talk about in a few minutes. And so therefore, the only way we can handle this problem is we need human auditors. We cannot escape from people. I mean, we cannot automate it completely. So let me quickly go over some basic notions of fairness that are out there in the literature. And then I'll try to give you some physical interpretation to each of these. So the first notion is called individual fairness. All it says is when two different individuals are similar to each other, the outcomes also have to be similar. Otherwise, that particular system is not fair with respect to individual fairness notion. So from a technical standpoint, T is the distance between the two individuals, xi, xj. And if it is less than kappa, then that particular classifier F is said to be kappa delta individually fair if the distance between the outcomes F of xi and F of xj is less than delta. Okay. Now, note that this is not a trivial exercise because number one, you need to compute the distance between two individuals. How do we even measure distance between two individuals? Because the question is what attributes matter and what metric to choose is a question that has been out there for us and people are still trying to resolve this issue. But the nice thing about this particular approach is it ensures equality. So when two people are similar, they get similar outcomes. If they're different, they can have different outcomes. That's the material, but similar people should get similar outcomes, right? But it doesn't address equity across sensitive groups, right? So for example, there are some groups out there in the society that require additional, support. So there are privileged groups on one side and you have underprivileged groups on the other side, which require additional support. So equity is also very important. Equality is not the only fairness criteria that we can rely on. So for the sake of equity, there is another standard notion called statistical parity, which says the outcome across, so the probability of a given outcome across two different attributes have to be equal. So if you look at attribute A and attribute A prime, so attributes are like sensitive groups, male, female, or you can define attributes based on race or a combination of them. And as long as you define these attributes in a certain way, across each attribute, this probability has to be equal. That's what statistical parity is all about. So it's more like equity. Okay. So in this example, so the probability with which A gets positive outcome is less than the probability with which A prime gets positive outcome, and therefore, from a statistical parity perspective, these two are not fair. Okay, so an example here. So now you can go further. In the case of binary classifiers, you can dig in a little further and define a few more fairness notions. And this is based out of this matrix here. I'll explain that in a minute. So equalized odds is about making sure that your false positives. So when the true label is 0, And when your classifier is detecting 1, that's a false positive, right? So the probability, the false positive probabilities, if they're equal across attributes, then that particular system classifier is said to satisfy fairness from an equalized odds perspective. Okay, that would be this case, false positive. Okay, you can do an equivalent counterpart to this equalized odds, which is called as calibration. So this is two positive probabilities being equal across attributes. So these are the various different fairness notions that are out there in the literature. And there is nothing new that we are doing here. And in fact, unfortunately for us, in order to improve this fairness notion, there is actually a trade-off between them. So in 2016, Choldachova was a PhD student, and she wrote a solo author paper. And then independently, Kleinberg, Mullainathan, Raghavan, in 2016, as a group, they came up with the same result, and the result is as follows. So imagine that you came up with a risk assessment that satisfies simultaneously statistical parity, equalized odds, and calibration. Okay, so these are the three statistical fairness notions that we just discussed. Now, the only way these three can be simultaneously satisfied is when your original classifier is coming up with perfect prediction, meaning zero error. It has to come up with a perfect prediction. Only then will these three satisfy. Or another case is they have to have equal base rates. That means it's as good as flipping a coin. So so other than these two scenarios, if you look at a more practical scenario where it is neither of these, you cannot satisfy all these three fairness notions simultaneously. And that is the fundamental trade-off between statistical fairness notions. And because of that, there's a huge fight in the fairness literature, as to, so if one fairness notion has been guaranteed, people will start questioning why this particular system is not guaranteeing the other fairness notion. So you see that here. And how do we mitigate algorithmic bias? In general, there are many different approaches out there. For example, in the case of individual fairness, there are auditing approaches. Okay, so people have used auditing to improve individual fairness. In the case of statistical parity, there is data pre-processing, meaning before you send the data into the algorithm, you pre-process the data and then send. And those techniques help improve fairness to a certain extent. And I'm giving you some example papers here, the titles here. This is no way a comprehensive list of papers that are out there. There are more papers than what I'm showing you here. And then another approach is to decorrelate sensitive attributes so that you can achieve statistical parity. That's another technique. And then you have post-processing techniques, meaning once you get the outcome from the machine learning algorithm, how do you tweak it so that you can ensure fairness across groups? Now, again, these are just samples of papers out there in the literature, but again, as I told you, this doesn't solve the problem because at the end, we do not know what the distance metrics are for individual fairness perspective, or even in the case of statistical fairness notions, we have this conflict. So which particular fairness notion is appropriate for which context is something that is unanswered. So which is why we need something beyond whatever is being done currently, and we are proposing something new, which is called as a non-comparative fairness notion. And the approach is this. So if you look at all the previous works, all the previous notions, they basically compare two individuals or two groups. Now, what we are saying is you can actually come up with a fair assessment without comparison. You can take a data point and then maybe an auditor, an expert auditor, can come up with F as a certain rule that he thinks is the correct rule to process X into Y. But the algorithm that we have, the machine learning algorithm, uses G instead. So the question is how different G and F are. And that is this particular, so when you compute the distance between G and F, and if it's less than epsilon, then you say, then the auditor would say that it's fair, otherwise it's not fair. Okay, so the same is explained in this particular picture here. The user profile is given, classifier computes G of X, and then auditor is given the same X, auditor computes F of X, compares F of X with G of X using the distance metric G, and gives out a fair evaluation. He'll tell whether this particular evaluation is fair or not. Okay. Now the question is, what's the relation to the what is the relation to individual fairness? Why are we doing this? Why are we coming up with a new notion? In fact, so just to give you some context here, individual fairness, as long as the distance between two individuals is less than kappa, the outcomes distance, if it is less than delta, then it's called kappa delta individually fair. Okay. So the first result that we had was, if G is epsilon non-comparatively fair with respect to F, meaning if your classifier is similar to the auditor's rule, and if the auditor is individually fair, then your system is also individually fair. So you can ensure that. So as long as you have the auditor being individually fair, and so okay, looks like I'm running out of time. I'll move on very quickly. So
yeah, it would be good if you can summarize in a couple of minutes.
I'll wrap it up. And then we basically show that what we have shown is, if you want individual fairness, you need epsilon non-comparative fairness. Without epsilon non-comparative fairness, you just cannot get individual fairness. That's the result that we have shown. So it's a necessary condition that you need to satisfy in order to achieve individual fairness. The same is true even for statistical parity too. If you want statistical parity, you have to have epsilon non-comparative fairness. If you don't have epsilon non-comparative fairness, you don't get statistical parity. So these are the fundamental theoretical results that we had. And then what we did was, we actually took our non-comparative fairness notion and applied it to three different real data sets. The first one is Compass, which is coming from criminal justice systems. The second one is adult income, which is based out of income. What's the income of a given individual. And the third one is German credit, which is coming out of banking industry from Germany. And we showed and we took some arbitrary rule, auditor rule F. So here is one auditor rule that we have chosen for Compass. This is the auditor rule that we have chosen for adult income. And this is the auditor rule that we have chosen for German credit. And we can clearly see what's the epsilon difference between the two, between the classifier that's used by in those data sets and our fairness rule. And you can actually measure the gap. And in fact, looking at this particular Compass is known to be known to satisfy equalized odds. So you can actually see that this gap is very small. So is the case with adult census. The gaps are very small with equalized odds. But when we look at the traditional literature, they have shown that each of these data sets satisfy one or more of these fairness notions. And you can see a similar pattern in our analysis. And currently, we are looking at how to measure biases in a new system or an auditor. Meaning, if you analyze a person or an auditor, a new auditor, or a system on some benchmark entity, then can you transfer these biases to a completely new application on a new data set? And it's not so trivial. And that's something that we are looking at. And the work that we have done, at least the first part of the work that we have done, was published in FactTrack 2020. So in summary, we have talked about trust in socio-technical systems. more specifically, we have talked about two projects. One is inaccurate mental models in the context of repeated tasks performed by workers. And we use discounted satisficing heuristic to model their behavior. The next one, we have talked about fairness, how to address biases in machine learning algorithms. And what's its relation? We proposed a non-comparative fairness notion. What's its relation to individual fairness and statistical parity? If you have any questions, I'll be happy to take them. Sorry for taking 2 extra minutes.
Okay, so let's thank Dr. Nadendla. It's time for questions. Yes, Ardhendu.
Hi, Sid. Can you see me or hear me?
Yes. I can see
Okay.
you. I can hear you.
Okay, that's great. Yeah, very nice talk. Thank you for describing it. So I was wondering about this sharp threshold of this beta equal to half, and why in the first part. And is it possible that like the beta and lambda are actually not identifiable because they are a product, right?
You are right, Ardhendu.
So
One of the
like BT minus.
Okay, so I did not present one of the results.
Maybe I lost. Yeah.
Can you hear me? Okay.
Yeah.
So
yeah.
I did not present one of the results that we found very recently, and the result is as follows. In fact, theoretically, you can show that there is no unique beta lambda pair that can give you the same stopping time for that model. And so, which means that there are multiple local minima,
right?
And you can change the local minima, and they explain the stopping time. You can predict the stopping time very accurately, but you don't get the accurate beta lambda estimates. And this is something that we have observed in many human decision models, not just this. I've observed this in another work of mine, which I've done back at University of Illinois as well. And uniqueness is a big issue that comes down to.
Right. Yeah, that's what I was thinking. I mean, that might be the case. And regarding the second project, like you described this new notion of non-comparative thing, right? So when in the definition, it is like G, whatever, G is your auditor and F is some rule. And so you need to measure the distance between G and F, or you're saying that the distance between G and F for all X in your input is less than epsilon, right? So how do we even compute that? Like, do we, like the set X is possibly infinite, right?
Usually in practical settings, the kind of X that we are looking at is discrete value. Where we are coming from, there are some data sets where some of the entries could be continuous. But in the practical examples that we have seen, so for example, comprise, the attributes are gender, race, offenses committed, number of offenses committed in the past. These are all discrete values, right? And so we never had this issue with the data sets that we dealt with. But you are right. Kleinberg's result holds true even for continuous data sets too.
Okay.
This approach would be difficult in the context of continuous value attributes.
Right. Yeah, I think in continuous valued attributes, there would have to be some sort of,
Let me rephrase that. So if your continuous valued attributes are bounded, then it's okay. If they're unbounded, that's when the.
Okay. Thanks. Yeah, thanks. That makes sense.
Other questions? So Sid, one question is that you talked about this fairness, and the first one actually had a little bit on the trust as well. But in this particular case, the fairness and trust, can you combine them? And there may be some trade-off, right?
We are actually, I mean, I don't have an exact way of combining trust with fairness, Dr. Das, yet.
Or a trade-off, whatever.
But the whole, I mean, the way I am coming at it is because fairness is just one reason why trust can be affected. So
right.
The way I'm looking at it is there are multiple reasons why trust can be affected. Fairness is one. You can have inaccurate mental models, and that can also affect trust. You
right.
can have misaligned motives, and that can affect trust. So how do we model one parameter that basically is a function of all of this? It's a very complex setting, and I don't have an answer to this yet. But the goal is to come up with one such.
It may not be a single parameter, right?
It may not be a single parameter too. I don't have an answer to that because it's too complex to handle that.
How is the complexity? Because most often this fairness, algorithmic fairness and all these things are time-wise quite intensive, right?
Right. So the traditional notions rely on comparative. Traditional notions are all comparative, and so you have to look at the entire data set as one batch. The approach that we are taking is more conducive to the online learning approach. So it's probably better because we are looking at one data point at a time. We don't have to worry about the entire data set using non-comparative fairness notions. So, I mean, coming up with those comparisons that we have towards the end for Compass and all the three data sets, that was very quick. But how does it really, how does it work when you apply it to learning biases? That's getting a little heavy in terms of so if you look at the idea that, I mean, I did not get much time to talk about that final thing that we are doing. So this graph that you have here, these are the sensitive attributes. These are all the attributes that are available in your data set. So everything to the left is your benchmark system. Everything to the right is the new system that you would like to evaluate. So this left system could be a system that's coming out of criminal justice. Compass is well studied, so you can think of this as Compass. And maybe this is some algorithm that you're using in real estate. The question is, can you transfer? So can you estimate biases in an auditor on Compass and use him to judge or evaluate a system in real estate markets? It's not so trivial, and that's what's taking a lot of time.
Are you looking at some of these transfer learning approaches?
It's not exactly transfer learning that we're doing. It's identifying what biases get transferred.
Okay.
So
other questions, please. All right, Sid, thank you very much. Do you have another question, Ardhendu?
Sure.
Ardhendu, you seem to be frozen.
Can you type?
Yeah, you can type on the chat.
Auditor rule, the experiment.
Ardhendu, could you write on the chat? I think your voice is breaking.
Yes.
Some of the connection probably is an issue.
Could have low utility. Trade-off.
And it's, yeah.
So yes. So there will be a trade-off between utility and fairness. So for example, utility, if you want to define it based on accuracy of machine learning algorithms, right? So you're trying to mimic your training data as closely as possible. That's utility. But fairness, on the other hand, is totally different, because there could be biases present within the data set, and following the data set blindly is not the best approach in this context. So there is some sort of a trade-off between utility and fairness. And there has been some study, some work in this trade-off. So there is this work by Kush Varshney from IBM, who actually did this trade-off. And they use that work in their AI 360 tool, which they deployed. So IBM has a tool called AI Fairness 360, which they have deployed, and it's used in that particular tool. You can look it up. But there is a trade-off. Yes, you are right. I don't know if I answered your question.
I got it. Thanks. Yeah.
Anybody else? Otherwise, Sid, thanks very much for a very informative talk and very like ongoing work, which is a lot of ideas and food for thought.
Thank you. Thank you.
Okay.